Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everybody, I'm Kaisar Chaudhary. I'm from Georgia Institute of Technology, and today I'll be presenting this work, that's the development of 3D stomach model for surgical planning. I have a number of people who assisted me in this work, and we have done collaboration from different institutions, including the Georgia Tech, the ECE department, the BME department, as well as the Emory University, Emory Children's Hospital, and last but not the least, Microsoft Research, Dr. Yanchi. Okay. This work is basically based on a disease which is very common in the infants of very less age. They are generally below 1 year old age, and the disease is called GERD, which is gastroesophageal reflux disease. There's a sort of a one-way valve in the food tube, which is either not developed in these infants, or there is some problem in this particular valve, and because of that, whatever food the infant takes in, it has the tendency, generally these babies are lying flat on the bed, or they're not standing upright. So because of the gravity, there is a tendency of the food to flow back through the food tube and come to the mouth, and this can result in choking and even in certain cases the death of the infants. And this problem is quite a common problem, and there are hundreds of surgical procedures done in one hospital per month. So our motivation behind this work was mostly to assist the surgeons in their pre-surgery planning, and in addition to that, we actually wanted to help the community and bring our research down to the last level where you have the clinical application of that. That's the main motive behind this particular results. And the issue with this particular stuff is that the surgeons only have the modalities like CT scans available to them to see what's already inside, or what's the state of the stomach of the child. And there are some good quality machines also available which can do relatively higher resolution of the CT scans, but generally under normal circumstances, the scans which are done are not very high resolution. Just to give you an example, a scan of an infant is shown in the slide. This is a 512 pixels by 512 pixels with an axial resolution of 10 millimeter. So with this resolution, there are around 20 to 25 axial slices of the stomach which you can generate out of the CT scan. Again, the contrast is not very good. They use specific contrast enhancing agents, foods to the babies. So you see a bright white spot around in the stomach region. That is basically to enhance the inner lining of the stomach, so you have relatively better idea of where the stomach is located. So the whole problem basically arises from very, very less amount of data which is available to you to create a model. As one of the solutions to this particular problem, we tried to find out what are the best data sources available, and there was a one-time effort by NCI in which they took a frozen human dead body, and they slice the complete body throughout its length and photographed each and every slice. This is a very high quality data. These are the colored images, and the resolution, as you can see, is 4,000 by 2,700 pixels, and the axial resolution is around 1 millimeter in the vertical direction. They have a even better data set which was introduced later. That is, this is for a human male, and then we have another data set which is human female that is 3 times the resolution of this. The 2D resolution is same, but in axial direction, instead of 1 millimeter cuts, they have 0.33 millimeter cuts. So this data has been used extensively by the medical imaging and the modeling community to generate different models and use them. But we have basically picked up this data set to gain knowledge from this model and apply this knowledge to the infant stomach model. Just a comparison of the two models, and because of the lack of space, the visible human model has been scaled down. But you can very well appreciate the amount of the detail which is available in this model. During my presentation, I'll talk over of how we developed the detailed stomach model based on the visible human data, and then how we started building the model of the infant stomach, and then some registration techniques which can be applied to one model to register it to another model to improve it. A few issues and related to these registrations, some results, and finally I'll conclude. Okay, first we tried to develop a good stomach model based on the visible human data. Although the definition of the images is quite good, and we can use some automatic and semi-automatic segmentation techniques. But as this was only a one-time effort, we could afford to spend time on it. So we wanted to ensure a best possible model. We went for semi-automatic manual segmentation, which was done and verified by multiple people. And we extracted both the inner and outer walls of these stomachs. And the data is around 300 slices. Out of those 300 is a quick snapshot of what are the various stages through the axial length of the stomach. Okay, to create the data model, we used the VTK, which is visualization toolkit, and the steps generally involved. First, we had to segment it and then convert this particular sequence of data into data format or volume, which is readable by the VTK, and then the standard volume rendering techniques were used to extract the skin surfaces and render them. And then we also had to put an interactor to manipulate the models and extract the data points out of the model, which I'll show you later. This is the snapshot of the model which was initially created from the visible human data. This long esophagus tube shown, and then using some of the filtering techniques to improve the model. The improved model is shown on the left, and I'll show you a video of this particular model. There's some opacity also imparted to the walls, so you can see the inner and outer walls within the model. You can zoom in and manipulate whatever way you want. The model is quite efficient. You can render it in real time and do any sort of manipulation at any zooming level. So the computational issues are not there. Okay, in case of the infant, the same techniques were applied, but you can see in this particular case we have only 21 axial slices of the images, and out of that I've just put 6 over here. But there are, between the consecutive slices, there's no real continuity, and you can see there are big jumps between slice to slice as the axial resolution is very low. So this basically hampers creating the model. The left two figures shown are the snapshots of the model. First, the initial creation of the model. You can see there are a lot of holes and missing areas because the normal surface rendering techniques cannot basically appreciate a big jump between slice to slice. So those are rendered as holes, and if you even filter them through the smoothing process and all that, the figure at the bottom is generated, and you can see the different views of this model as well, that how coarse and how bad the model is at this particular stage. You really can't make out different features of this particular model. The next step in the development of model was to basically somehow or the other register the two models, bring them close to each other, and plug in the information which is missing in the infant stomach from the visible human model. To do that, the general approach is to first rigidly register the two bodies, bring them close enough, treating them as rigid bodies, and then do the non-rigid registration techniques to basically deform one of the models to fit the other model. Just a simple example, if you have two bodies which are quite similar, the only variation is primarily in its rotation and the scaling. So you can basically rotate, I'm rotating the second object and scaling it so that it matches the first object. Most of the areas are aligned, but if you see that sure how this works. Anyway, the left line, which is a zigzag line shown in the black color, and that is the area which could not be captured by the rigid transformation. So you'll use the deformation techniques to bend this, one of the bodies to map the other. So to come up to use this particular approach, you need basically anchor points on different models, which gives you the relationship between the two bodies, so you can compute your parameters for rotation, scaling, and all that stuff. So it's easy for a two-dimensional stuff, but in 3D, you have the display, which is also a 2D. So when you are moving a mouse pointer over the model, it is not basically corresponding to one particular point in the 3D model. So there's a specific technique which is called point and shoot method, which is basically going to shoot a ray from your mouse pointer onto the model, and the first point is going to hit on the surface will be taken as the data point. So using that technique, we picked up different points, about 5 to 6 points which correspond to each other in both the models, and then tried to register the model. But as the two models were not from one subject, there were significant variations between the two models, so certain issues came up, which I am going to highlight using this particular example. Now, these two objects are somewhat closer to each other, but definitely they are not from the same. They are not the same object. So if you try to do the rigid registration of these particular objects, the closest which you can get is something like this, in which your blue dots between the two objects are somewhat aligned, but and overall structure is mapped on top of each other. But if you try to bring both the red points together, you are going to warp the complete object, and it won't be useful for your next step, that is the non-rigid registration. So issues like that were also seen in this particular models. So if you bring them to the best possible limits without wrapping the models, in certain places you have your alignment as shown in the left figure. The two models are sort of aligned, but they are separated in the translation space. In the other, they are close as far as their centroid or the translation is concerned, but their orientation is different. So in one go, you can't achieve this particular task. So you have to go by, in addition to that, there's a lot of variation between two models. There are places where one contour from one model maps to two different contours in the other model. So these type of issues are there, which hamper the construction of model and the registration of the two models in the normal way. As a solution to this particular problem, we did local registration of the two models, and we went by piece through the model to register them, and we used the normal morphing techniques using the surface normals similarity. And this is one example, just a layman example of how we can morph a circle into a square, and there's an intermediate step shown. But this technique was basically used. Even if you don't consider the visible human model, right from these are the consecutive slices of the infant stomach shown. There are certain cases. The first case is you have, in one slice you have one object, in the second slice you have one object, so it is easy to morph between the two. But the second case, which is the top right, you have one object in one slice and there are two objects in the next slice. So the algorithm has to automatically decide whether it is going to take one object and spread it onto the two, or map one to one and leave the rest one. So based on their location and other similarities, we have to take that particular decision. Then you may get 2 to 2 slice correspondence and 2 to 1 correspondence and things like that, which are all information was extracted from the visible human model and imparted to our algorithm to make the decisions based on the fine model. and do the morphing as it is shown. I'll show you a quick video of if you have one particular object and just in one case there's one object, in the other case you have two objects. You're basically trying to merge the two objects into one and then do the morphing to create or merge into the other one. So using the information from the visible human model as well as some morphing techniques, we were able to improve the model. And you can compare the initial starting model and the improved model which we generated for the infant stomach. This video also shows you the different views of that particular model. Although this model is not as good as the one shown for the visible human, but if you compare it with the available information content, just a quick flash for the comparison. This is the only information content available to you for creating the model at the start. And if you come up with a model like this, it certainly helps a lot to the surgeon for planning. So he exactly knows what is going to expect when he is going to start the operation. But in under normal circumstances, if there is a significant abnormality, that can be detected in the CT scans. But other than that, when the surgeon starts doing the operation, only then he is exposed to what is available to him, and what he has to do is he has got very less time, because even in this particular case, the infants are, cannot be given anesthesia for a longer duration, so the time constraints and all those things. So even these type of models are helping them significantly. So just to conclude, we have been able to develop the model which is good but not very good, and our next phase is to further improve them using better techniques, as well as to create the deformable models which can be manipulated using devices like haptic devices, and to do virtual surgery before even going for the actual surgery. Then I will acknowledge the support of different institutions for this work, including the Georgia Cancer Coalition, Georgia Research Alliance, and Microsoft Research. Again, if you have any questions.
Thank you.
Are there any standards for that tactile device? You mentioned there might be a tactile device.
Haptic device.
Haptic, yes.
Yeah.
Tactiles, either.
Yeah.
Are there any web standards for that, or is that individual for each case?
There are no standards right now, but it is being used for certain models. Mostly they are physical models which have in which the measurements can be done, the spring constants and all that can be measured, but so far from the biological area, we don't have, at least I have not come across any of the models which are being tweaked by the haptic devices.
I have a question. Have you talked to the clinicians? Did you get any comments from them about this model yet?
The final model we have not yet, but during the course of the development,
yeah.
they have been involved, and they were even happy with the initial model, so definitely they will be much happier with these
So it's definitely
latest.
valuable
Yeah,
for them. Yeah.
Yeah.
Yeah. Any more questions? All right, that concludes our session. Thank you.